So the idea for this kind of stuff is that maybe different parts of the object, different positions, will have differing amounts of force on them, like in the spring example. Or maybe different parts of the object will all have the same amount of force on them, but they have to go a longer or shorter amount of distance. Well, gosh, what if it was both? What if different parts of the object both had differing amounts of force on them and had differing amounts of distance to travel? Well, what on earth would have that going on? So let's say we want to drain a tank, the kind that holds water. So how are we going to calculate the amount of work? I'll give you a spoiler. We're going to slice this up and model the individual pieces of, well, water here, the individual slices of this cone. And we're going to ask for each one of the slices, how far do we have to travel? And also, how much force is acting on that piece? So perhaps if this helps the imagination, my tank of water is frozen solid, and I'm going to chisel out a layer and pull it out, and that's outside of the tank now. And then I'm going to chisel down the next layer, and I can pull that out, and each one of those will be some particular amount of work required to move. And I would like to move all of the water out of the tank in that way. Now, realistically, I wouldn't actually freeze my water before I try to move it anywhere. But the idea remains the same. In my head, I can chop up this tank of water. And in my imagination, the sliced up well does not spill. I am doing this so I can calculate the amount of work required to move every different slice. Okay, well, let's figure that out. So setting up the problem, we actually need to have some numbers going on. The shape of the tank is a cone whose height is 10 meters and whose radius is 4 meters. It's filled up to a height of 8 meters. What we are going to do is we are going to pump all of the water up to the very top of the tank. And for our information, the density of water is 1,000 kilograms per meter cubed. Okay. Well, I want to put all of this together to be able to just calculate the amount of work to move this purple slice up and out of the tank. If I can do just this slice by itself and get a nice formula, I can find the work required to move any slice, and then I just add all of that work up together. Okay. So let's say that our x-axis has once again been put on its side like so, just to make things simpler. And what we're going to do is we're going to say 0 is at the very top, and maybe my x here is measuring depth. Maybe I've dug this out of the ground, if that helps make the coordinate system a bit more justified. If I'm starting at coordinate x, and I'm trying to get all the way up to coordinate 0, then this slice of the water has to move x units. Okay, cool. Well, where is the water? If the water is 8 meters deep, well, then the very deepest point is x equals 10. The very surface of the water has to be x equals 2. So as I go to slice this up, I'll be starting at x equals 2 and finishing at x equals 10. Those are going to be the bounds for my integral. Now, I need to find the amount of work required for every different slice. So I need to find the weight of that water, right? And I need to find out how far it goes. I already know it goes a distance of x. So all I have left to do is to find how big is this slice exactly. Then I'll use my density of water to finish up the job. So my radius, right, Ri, is the radius of this slice, and my thickness, delta x, is the thickness of the slice. Those two numbers together should give me the volume of my slice. Here, because I know a cutaway of my cone will be a triangle, the very top of which has a base of 4. And down here at coordinate x, I need to find my corresponding radius. Well, we can just use similar triangles. So 4 by 10 is the dimensions of the big triangle. Radius r by, looks like 10 minus x is the dimensions of the small triangle. So r divided by 10 minus x should equal 4/10. Right? That is my similar triangle that the ratios of these base and height numbers should be the same for similar triangles. We'll rearrange and say that the radius is equal to 2/5 of 10 minus x, which says that my volume should be pi times that radius squared times my delta x, and here is that expression written out. And I'm going to multiply it by the density to find its mass. Right? The density of water, they told us a couple slides ago, is 1,000 kilograms per meter. Altogether, we have this amount of mass, which will be 160 times pi times quantity 10 minus x squared, depending on what x coordinate we pick. Excuse me. And again, here our delta x is dependent on the width that we chose, the thickness that we chose. Okay. So force is equal to mass, which we just found, times gravity. So in scientific standard, we're going to use 9.8 as our force of gravity. So each individual part here will have 1,570 pi times 10 minus x, that quantity squared, times delta x. That is the amount of work, not force, not force. It should be work on this slide. Goodness. This is the piece of individual work. We're going to add them all up. Oh, I see. Yes. This is my mistake for working off somebody else's slides. That is the amount of force, excuse me. But then each layer has to move exactly x coordinates, so we're going to multiply by an additional x there. Okay, well that was a lot, but we've got a formula now for the amount of work we're going to do. And we're going to add all of those pieces of work up for a finite number of slices. That would be just an approximation, but in the limit, this becomes an integral. So my work integral, my integrand, is telling me what is the amount of work used to move an infinitesimal slice of the well water, I should say. And once again, we have a very simple integral of a polynomial. I can just move my constants out to the front for the time being. And this comes out to be exactly 1,570 pi times 2048 on 3. or approximately 3.4 million joules.